Hello, hello. Welcome to our first biology lesson this year. Glad to have you. So if you're joining us, I'm guessing you either missed the notes or want to see them again. So let's get to it. We're in Unit 1. First bit of notes here. In this first unit, we will be discussing lipids and early cells. That's our Unit 1 title. Our first section that we're doing today, we're going to look at elements, compounds, and properties of water. All right, so getting into it then. So everything in the universe is made of atoms. Atoms are considered to be our basic building block of all matter. So everything we're going to work with is made up of atoms. When you guys take chemistry next year, you learn that atoms don't really look like this. It's kind of like a marble. There's a bit more to them, but for right now and for this class, we can visualize, we usually will, atoms as kind of just a marble. It's a lot of times how we think of them as looking. So there's an atom of carbon, it's kind of a marble with a C on it for carbon. One step up from atoms, so atoms often link or bond to other atoms to form what we call compounds. So compounds are two or more atoms linked together. A couple of examples for you here. So there's sodium and chloride, and they are bonded together. They're stuck together. This is a compound. This one is commonly known as table salt. Its formula is NaCl. There's our first compound. Two atoms bonded together to make a compound. This compound is called table salt. Another example, pretty common one. You are exhaling it now as we speak. Carbon dioxide. And there again are the bonds holding the two oxygens to the carbon in the middle. And again, the whole structure here is what we call a compound. And this one specifically is carbon dioxide. Pretty familiar compound to us, CO2. All right, I'm going to leave kind of a blank spot in the middle here. I'm going to come back and fill that in just a second. For right now, though, that we're kind of seeing are two types of bonds, at least the two types we'll work with most often in this class. So compounds are usually now, this isn't always the case, because we'll take chemistry next year and learn that there are other types of bonds. The compounds are often either They're either ionic bonds, which is a bond between two oppositely charged particles. So I don't know if you guys noticed, I drew that plus symbol above the sodium and the negative symbol above the chloride. It's actually that positive and negative that creates the bond that holds these two atoms together. Or we also often have covalent bonds. Now, another term for covalent bonds are molecules. Probably heard that term before. Molecules is specific to covalent bonds. I'm not saying you won't ever hear it referred to like a molecule of table salt, but most technically, molecules refer specifically to covalent bonds. And these are So these are shared bonds between atoms that usually involve little to no charge. So in these ionic bonds, the whole thing that holds them together is that positive and negative charge. Whereas in a covalent bond, they're sharing the bond and there isn't much of a difference between them. We don't have that positive and negative charge. And that's what leads us to our hero today and our hero in life, water. So water is kind of a superhero compound. The reason why I call them a superhero compound, well, life wouldn't exist without them, and we'll cover that over the next couple of units here. But the reason why it's a superhero compound, is water is a covalent molecule. It has covalent bonds holding together the oxygen and the hydrogen, but it also has charges. So it's a little bit of both types of bonds. He's going to fit right in between. And that's why he's such a hero. He's such a unique compound in that he can kind of do both. He can have properties of covalent molecules and of ionic compounds. When we have this type of compound, we tend to call it polar. So there are some other polar molecules, but water is the big one. So I'm going to go back up here, the space that I left earlier, and I'm going to squeeze in a molecule of water. So there's our covalent bonds. We've got the O covalently bonded to the H's, but it also has charges. The oxygen has a delta negative charge, and the hydrogens have delta positive charges. This looks like a lowercase d with a flag. It's actually the Greek letter delta, and we use it here to mean a partial charge. It's not a full charge. Here's a full negative charge. Here's a full positive charge. For our water molecule, it's only a partial negative and partial positive. So it's not a full-on charge, just partial, and that's what we use that little delta symbol to represent. And again, this type of molecule we call polar. Think of like the poles of Earth, the North Pole and the South Pole of Earth, like opposite poles. Well, the same thing for water molecule. We've got a north end, a negative end, and a south end, a positive end. So it's a polar molecule. Some of the traits that we get from water due to that polarity So due to its polar nature, water can, we've got a list of several things that water can kind of do that a lot of other compounds can't. Again, because kind of half ionic, half covalent, kind of right in the middle there. And one of the things it can do is it can form what we call hydrogen bonds. Oftentimes we just call them H bonds. H stands for hydrogen. So we kind of simplify it, don't have to write the whole word hydrogen and just write our H bonds. So what those look like. So we have our water molecule, and say we have another water molecule right here, and it's also got that delta positive and delta negative. Well, opposites attract. So just like with the ionic bond, this negative side is going to be attracted to the positive side. And that right there is our H bond. Kind of important to note, it is not as strong as an ionic bond, which is a good thing. If it were as strong as an ionic bond, we'd have problems breaking them apart. And this is one of the reasons why water is a liquid at room temperature. So most small compounds, most small molecules, carbon dioxide, methane, oxygen, nitrogen, carbon dioxide, these are all small molecules and they're all gases at room temperature. Water is a liquid. It's kind of held together. These hydrogen bonds keep the molecules held together, and that's why it's a liquid. They're not held together so tightly that they can't move, and that would be when it would become a solid. So if we get the temperature down low enough, we do often have solid water, but at room temperature, water is a liquid. Ionic compounds tend to be solids at room temperature because they're held together really tightly and the molecules can't move around. So this is not as strong of a bond. It's kind of a weaker bond, that H bond, and so it allows the oxygens and the hydrogens to stay connected, but still move around a little bit. Liquid. So our H bonds, that's kind of our first property that we have there. Another property, due to that negative and positive interaction, so another thing that water is able to do, due to its polarity, that positive and negative end, is it's able to interact with other positive and negatively charged particles. For instance, dissolving salt. And what salt looks like when it dissolves, you guys have all seen that white crystalline structure go into water, and voila, you can't see it anymore. It's dissolved. It didn't disappear. It's still there, but it has dissolved. And what dissolving is here we have that bond. Here we have those two stuck together. And you get a whole bunch of them stuck together. It's that large white crystal that we see. But when it goes into water, the water molecules pull each of those atoms apart. The negatively charged oxygen likes to be close to the positively charged sodium. So the oxygens surround the sodium. Like that. And kind of somewhere else, not together, we have the negative end of that molecule, that compound, that salt crystal, and the positively charged hydrogens will be surrounding that side of it. So those positive ends are going to be one near the negative end. So we end up pulling that salt crystal apart. So where does salt go when you put it in the water? It doesn't disappear, it dissolves. What is dissolving? Well, it's those individual ions being pulled apart, being pulled in different directions. They're now so small that we can't see them. We can't see these individual ions or atoms in the water. We just don't see them. And that's what we call dissolving. The same boat here, same level, but the exact opposite. Oops. So by contrast, non-polar compounds, for instance, carbon dioxide, CO2, we took a look at him at the beginning, they're not soluble. They don't dissolve, and they tend to minimize their contact with water. They don't want to be anywhere near water if they can help it. No, sometimes they can't help it. We like to make carbonated beverages, soda, carbonated water. One thing a lot of those carbonated beverages have in common is bubbles. So exactly what are bubbles? Well, bubbles are the carbon dioxide minimizing their interaction with water. So you can imagine a whole bunch of carbon dioxides forming a whole circle. I can't draw a whole circle, I'm out of room. I'm not sure I could anyway. It's a lot of carbons and oxygens to draw, but imagine they go around in a big circle. What that does is when they're stuck in water, it minimizes the amount of contact they have to have. You can imagine just one of these guys being in water, just one carbon dioxide. Well, the water molecules would completely surround it. Nobody would be happy. The water doesn't want to be near them. The carbon dioxide doesn't want to be near the water. No one wants any of that. But by kind of forming this circle here, they can minimize their contact. Now only one part of them has to be close to the water molecules. So water molecules are surrounding them. The carbon dioxide, yes, there is an edge of them that is going to have to interact with the water. But a lot of them on the inside here get to stay inside, get to stay dry, and they don't have to have those interactions, which they don't want. And this forms what we call bubbles. And that's what we see when we see those carbonated beverages, when we see those bubbles, they're collections of carbon dioxide just kind of grouping together so that they can minimize their exposure to the surrounding water molecules. And that's what we call a bubble. All right, nearly done here. Should be the last page. We're on. So water is a very abundant molecule. It is the most abundant molecule in cells. You can take a look at any cell anywhere that we know of. Roughly 70% of that cell by mass would be water. So water is incredibly important in biology. As we talk more and more about cells, a lot of what we're talking about are the interactions that the different parts of these cells have with water. So those interactions between water and the other constituents of a cell is going to be a really important thing we discuss as we go through the year in biology. Really important, and so that's why we take some notes on water. We have a good understanding of what we're looking at, why some of our compounds are behaving the way that they do. One last little note here. Most of the rest of a cell outside of water, so if you could dry out a cell, if you take all the water out of it, most of the rest of that mass is comprised of 4 classes of what we call large molecules. The Greek word for large is macro. So our macromolecules, those 4 classes are lipids. We'll start the title of this chapter. Nucleic acids, proteins, and carbohydrates. And honestly, this first semester we're working with here is going to deal a lot with these 4 macromolecules. They make up most of life. All right, so that ends our first bit of notes here. Hopefully the next lesson we'll get to tomorrow is a little bit shorter, but hopefully this helped. I'll see you guys next time for 1.2. Signing off.